Let's define a few terms before proceeding. We can categorize indexes based on their effect on file organization, based on search fields, and based on data representation. If a file is organized in a way that data records are ordered in the same way that data entries are ordered in an index, the file is a clustered file. An index file organization is a clustered file by definition. But a data file with separate index files has a clustered index if its data records are sorted on the search key field of the index. Otherwise, the index is unclustered. A primary index is an index on a set of fields that includes the primary key of a relation. A primary key guarantees that there are no duplicate entries for the same value of the search key. An alternative naming convention is also in use in the field that defines a primary index based on data record location on file. However, since we use the naming convention of the index file for this definition, we will use the naming of primary index as an index on a set of fields that includes the primary key of a relation. We also have dense and sparse indexes. In a dense index, we have an index entry for every data record. However, sparse index includes index entries only for some of the data records. Indexes either work based on some sorted order of data values, or they're hashed, meaning they work based on distribution of field values across a range of buckets determined by a hash function. Two common types of indexes accordingly are hash-based indexes and tree-based indexes. In hash-based indexing, data records are grouped together in buckets. A bucket usually has a primary page and additional pages that are linked to it. The bucket for a data value is decided by applying a hash function. In tree-based indexing, records are organized in a tree-like structure in a sorted order by search key value. Using the tree structure, searches are hierarchically directed to the leaves, pointing to the correct pages of data entries. B+Trees are the most commonly used index structure. While exploring indexing and index data structures, we evaluate indexes on how they are fit to a specific database application. This is based on different factors such as supported access types, access time, insertion time, deletion time, and space overhead. The types of access that are effectively and efficiently supported is an important factor for an application. Access types can include finding records with a specified value for an attribute, or finding records with attribute values within a specified range. Access time, which is the time it takes to find one or a set of data records, is also important. Insertion and deletion of records need to be efficient. Insertion time includes the time it takes to find the correct place to insert the item, performing the insert of the new item, and the time it takes to update the index structure to reflect the change. Deletion time includes the time it takes to find the item to delete and the time it takes to update the index structure accordingly. It is also important that the additional space we are allocating to the index structure is within an acceptable range for the cost to worth the performance improvements.